Greetings and welcome to STEM Smart Academy, where in our live session today we are going to handle this topic called being taught in physics and on the medium of transmission. We have those waves that require a medium for transmission and those that do not require a medium for transmission. Our first type of waves is what we call the electromagnetic waves. Dear learners, when you talk about electromagnetic waves, these are waves that do not require, underline require, a medium for transmission. A medium for transmission, and those types of waves we put them under what we call a medium for transmission. So you have to know that a mechanical wave, we do have what is called the water waves and the sound waves. That is why we say sound cannot be transferred through a vacuum, meaning that there must be a medium through which the sound is being propagated. Now, these mechanical waves transmission can be further classified either as transverse or longitudinal waves. Vibration of transverse or longitudinal, the vibration of particles will be perpendicular. It will be like this. This is an example of a transverse. That is an example of a transverse wave. You can see for me is what is meant by that point. Or you can use the term perpendicular. Kindly make sure that you subscribe to STEM Smart Academy if you are yet to. Now, dear learners, let's look at how are these transverse waves propagated. We all get to know that when you tie a spring or a rope flow on a bench, on one end is attached to a rigid support, while on the other one is held on the hand. The end held in the hand is swung up and down at right angles, like this one here you can see. There will be formation of a transverse wave. A transverse wave, regions of crest, the maximum displacement on the positive side of the mean position, or a trough, that is the maximum displacement on the negative side of the mean position. You need to know that, dear learners. You need to know that, dear learners. So the formation of crest and troughs is in the transverse wave. Look at this diagram on the right hand side. You can see the direction of the wave motion is horizontal and the displacement of the particle is vertical, such that this angle here is perpendicular, 90 degrees. It is at right angle. Now, we also have, because we've talked about the transverse wave as waves whose vibration of particles is at right angles to the direction of the wave travel. What about what we call the longitudinal waves? Longitudinal waves, dear learners, are waves whose vibration of particles is in the direction parallel to the direction of the wave travel. It is not perpendicular. For longitudinal, the direction of vibration of particles is parallel to the direction of the wave travel. And the example of a longitudinal wave, we can have what we call what? The sound wave. We can have what we call the sound wave. Look at this case. To illustrate the formation of a longitudinal wave, we simply use the spring is stretched along the floor or bench. One end is fixed to a rigid support and the other held in the hand. This end is vibrated in a to and fro movement continually along its length as shown. You can see. So a longitudinal wave, learners, is characterized by formation of regions of rarefaction and regions of compression. What are these regions? When I talk about a region of a rarefaction, this is a region where the spring tends to have been pulled far away from each other. While a region of compression simply refers to a region where the spring tends to be compressed, to be pulled, to be pulled, to be pushed together. We are squeezing the spring, giving you a region of compression. You can see how these are being concentrated here and how these are quite far apart. Now, we have also to look at this. Let's look at it under diagrams. In this case, we are looking at the longitudinal and the transverse wave. The first scenario here, this first scenario is for a longitudinal wave. You can see regions of rarefaction where these ones are far apart, and you can see where the concentration is high is a region of compression. A region of rarefaction, we can also call it a region that has low pressure. Low pressure has been exerted to it. While a region of compression is a region with higher pressure. When you exert higher pressure from both ends, you tend to compress the spring. Therefore, that end, dear learners, we tend to call it a region of compression. Look at your longitudinal wave, sorry, your transverse wave. This on bluish is what we call the transverse wave. Is what we call the transverse wave. It's called the progressive waves. What are progressive waves? These are waves that continually move away from the source. We call them the progressive waves. From the word progress, making a step. So the waves that move continually away from the source are called progressive. Progressive waves can be longitudinal or transverse. Can be longitudinal or transverse. We all know that if a stone is dropped into water surface, the resulting water waves moves outwards. It moves outwards, carrying the energy of the impact away from the source. Carrying the energy of impact away from the source. And remember, the waves that move away from the source are called progressive waves. The energy is spread over an increasingly large area. This causes a gradual decrease in its amplitude. We are going to look at what an amplitude is shortly in our definitions of terms. Then we do have also what is called a pulse. A very common question. You can simply be asked, learners, what is a pulse in waves? What is a pulse in waves? So, don't forget to link up to what a pulse is. To link up to what a pulse is. Learners, when you look at this case, a pulse is generated when a single vibration, underline the term single vibration. When a single vibration, then that is what is called a pulse. Also, it can be longitudinal or transverse. But for it to be a pulse, it must be a single vibration. A single vibration. I'm seeing people tuning in. That is good work. I can see Deborah saying hi. Wonderful. You can also see, I don't know, this person has got the name Jay saying hello. That's great. You can also advise your other friends to join STEM Smart Academy. Wave trends are generated as a result of continuous vibration at a constant rate in a medium. Now, we have what is called the characteristics of the wave motion, which is something very, very important. Now, you can see that the characteristics of a wave motion can be explained with reference to the oscillatory motion of a mass attached to a spring or that of the bob of a swinging pendulum, shown in the two figures below, figure A and figure B. In figure A, the mass of the oscillating spring, you can see the spring will be moving up and down. So that one will be longitudinal wave. So this one here, the first one here, is trying to give us an illustration on longitudinal. While B here you move from this to the other side. It is an illustration of what is called trans transverse. So you need to get the differences there, learners. You need to understand. Now, if for example the mass starts at M, look at figure A where M is, then M is not a complete oscillation. M is not a complete oscillation. This is because although the mass has returned to its starting position, it is moving in the opposite direction. For the pendulum, the bob makes a complete oscillation when after an initial displacement to say position X. If it starts position X, it swings from X to Y, Y to Z, back to Y, and Y back to X where it began from. So that will be what is called a complete oscillation. From X to the middle Y, then to the other side Z, from Z again to the middle Y, then to X, which was the starting position. So that one will be calling it one oscillation. Similarly, let me explain using this figure A. If the spring was pulled and began moving from N, for example, it has to move from N through M to L to M back to N. That will be a complete oscillation. A complete oscillation. Dear learners, you simply need to know these differences well, because at times learners get mixed up, and I'm here today to simplify them here for you. Let's look at the terminologies used in waves. The first term is what is called the amplitude. This is the maximum displacement of a wave on either side of the mean position. When I talk about the mean position, I'm talking about the position at rest, of rest. Some books in integrated science call it the position of equilibrium. So the maximum displacement of a wave on either side of the mean position is what is called the amplitude. Because it is displacement, therefore its SI unit is meters. Then we are being referred to in figure 8.7a, the amplitude is the distance LM or MN. Let's look at it. The mean position, remember M is the mean position. So from M maybe going up here, that can be amplitude, or from M going downward here, from the mean position, this can also be amplitude. Similarly, they are also saying in figure 8.b, the amplitude is simply the distance xy or yz. So this xy can be amplitude, or yz can also be termed as amplitude. Can also be termed as amplitude. Now let's look at this scenario here. They are saying for the pendulum, the bob makes a complete oscillation after an initial displacement, say x, it swings x to y to z to y and back to x. That is when you will say it has made a complete oscillation. You can see in figure 8.7, if the mass in A 8.7a takes 2 seconds to make a complete oscillation, a sketch of displacement for the motion will appear in a similar figure shown below. You can see this one here well represented. We are going to look at it. We need to understand the meaning of the term. Maybe let me give you a diagram here. Assume this is my transverse wave. If this is my transverse wave, dear learners, then what I want you to know, the distance, the maximum displacement of a wave from the mean position. The mean position is this horizontal line. So this maximum displacement here is the amplitude. Can be on either side, remember, underline the term on either side. So it can be on the positive side or even on the negative side here. So for example, If this reading here was 5, and this other reading here is -5. If you are asked the amplitude here, that is the maximum displacement, you could term it as 5, maybe centimeters, if the units given there were in centimeters, dear learners. Yes. Nishatoka tuko live nani hapo, sita tupigie 5 ama 450. Okay. So dear learners, that is how you identify the wave. That is how you identify the amplitude, the amplitude. That is the maximum displacement of a wave on either side of the mean position. And its SI unit is meter. Let's look at term number 2, what we tend to call the frequency of a wave. Frequency, which is denoted by small letter f, is simply the number of complete oscillations made in 1 second. The number of complete oscillations made by a particle in 1 second is what's called frequency. Its SI unit is hertz. You can call it hertz or cycles per second, the number of complete oscillations. When I talk about oscillation, I'm simply just talking about a cycle. So the oscillations or a cycle made per second is what is called a frequency. Its SI unit is hertz, or you can talk of it as cycles per second. Cycles per second, dear learners. We will look at its case later on. Then we have another term here which we do call the period. And we say that the period t of oscillation, this is the time taken by a particle to make one complete oscillation. The time taken by a particle to make a complete oscillation is what is called period. And because we are talking about time, learners, because there is one thing I want you to understand, learners, here. What is the SI unit of time? In integrated science grade 7 or in physics form 1, you talked about SI units. The SI unit of time is second. Remember, SI units are given in singular, learners. It can be S is second and its unit symbol is small letter s. So you need to understand this. Now, there is a relationship existing between frequency and periodic time. And that relationship, dear learners, you need to know that frequency and periodic time, which is denoted by capital, are inversely proportional. What do we mean when we say inverse proportionality? F is given by 1 over t. Similarly, one can say t can be obtained by saying 1 over f. T can be obtained by taking 1 over f. Let's look at the next question, learners. Let's look at the next question, learners. Not really the next question, but the next part. So this relationship between periodic time and frequency is very important as you keep preparing yourself for your exams. You must know f is given by 1 over t, or t is given by 1 over f. Inverse proportionality. So let's look at another term which we call wavelength. When you talk about wavelength, how best can we define the term wavelength? It's defined here. The distance between 2 points, not pins. This should be between 2 points on a wave that on a wave train which are in phase. That is what is called wavelength. The distance between 2 points, the distance between 2 points on a wave which are in phase. We can define this wavelength using several definitions, though I didn't capture them all in my notes here, but let me say them here. We can define wave as the distance between two successive crests or troughs. From B here, these are crests. So the distance between two successive crests here is what is called wavelength, denoted by the sign lambda inverted y. Or we can also define the term wavelength as the distance between two successive troughs. The distance between two successive troughs. This one can also be defined, that one can also be wavelength. That is for a transverse wave. What about for a longitudinal wave? How can we fit our definition to fit there? We can say a wavelength is simply the distance between two regions of rarefactions or two consecutive regions of compression. It must be two consecutive regions. It says that you say two consecutive crests or two consecutive troughs or two consecutive regions of compression or rather rarefaction. Now, because this is distance, what is the SI unit? The SI unit for wavelength is also meter. Because we are talking about distance, that is length, whose SI unit is meter. So you can see, so BD, from B to D, that's one wavelength, because they are regions in phase. Or EF, that's also a wavelength. That's also a wavelength. Let's look at what is called speed, or what in some cases we do define as velocity. We do term as velocity here. The distance covered by a particle in 1 second is called speed. The distance, remember, mathematically your teacher must have told you that speed is given by distance over time. So that means the distance covered by a wave in 1 second is what is called speed in 1 second. Therefore, the SI unit for speed is meter per second. And in this topic, we will be using letter V to denote the velocity here. We will be using letter V to denote velocity. We are going to look at it better when we get into some calculations, learners. Let's look at what is called periodic time in wavelength diagrammatically. You can see what a wavelength is. You can see the wavelength. Then the time taken to make a complete oscillation is what is called time period. The time taken to make one complete oscillation is what is called periodic time. Is what is called periodic time. The time taken to complete one. There exists a relationship, learners, between speed, wavelength, and frequency. That relationship is very important when we get into numerical calculations. It will be so much important. I hope you are ready for it. Look at this case. They are saying speed is given by distance over time. Everyone knows that one. Speed being given by distance over time. That one we know it from mathematics. So if speed, learners, is given by distance over time, we also have to know that for one cycle of a wave, then the distance being equal to lambda and time equals to t, then it means that our speed will be given now by the distance, which is now lambda, over the time t. By the fact that we know that speed is given by lambda over the time t, but remember, we know that t is equals to what? 1 over f. Remember, t is equals to 1 over f. When you have lambda over t, this is like saying lambda divided by t. So this will be like saying lambda divided by, this is 1 over f, because t is equal to 1 over f. So this is like saying lambda divided by 1 over f. And if that is the case, so my velocity will be given by lambda. The division sign changes to multiplication. Then this one reciprocates. 1 over f becomes f over 1. So this can finally be worked out as v is equals to lambda f. A very, very important formula. We call it the wave equation. This one we do call it v is equals to lambda f. We call it the wave equation. We are going to use it so much. So it's my request, learners, that you should be knowing that formula. V is equals to lambda f, and I have even derived it for you. I have derived it for you. Yes, it's even written here. We call it the wave equation. The wave equation, and it relates the speed of the wave to its frequency and wavelength. The speed of the wave to its frequency and wavelength. Okay, let's look at the relationship between wavelength and frequency. While the rate of vibration of the source determines the frequency of the wave, the speed in a given medium is always constant. From the relationship that V is equal to lambda f, an increase in frequency results to a decrease in wavelength. When frequency is higher, the wavelength is getting reduced. So that gives you such a type of graph. When frequency is high, wavelength is low, and vice versa. Let's look at how to identify phase and phase difference. Waves can be of the same amplitude. When you talk about an amplitude, remember, this is the maximum displacement of a wave on either side of the main position. So, waves can be of the same amplitude. Waves can be of the same amplitude but different frequency, or same frequency but different amplitude. Look at this first case here. I'm talking about, maybe allow I call this one here my case 1. When you look at my case 1, the waves all have the same amplitude. What about the frequency? Is their frequency the same? No. You can see here we do say these are waves of the same amplitude but different frequency. Remember, frequency is the number of vibrations. There is one that is moving very fast, that means it has a higher frequency, and there is that moves very slow, meaning it has a lower or a low frequency. It has a low frequency. Look at this case number 2. When you look at case 2, learners, the waves have different frequencies. This one has a frequency here, this one has a frequency here. They have different amplitudes. This can be amplitude 1, this has amplitude, maybe amplitude 2. So they have different amplitudes but the same frequency. Different amplitudes but the same frequency. So we can talk about masses oscillating in phase. In phase meaning that they move together. Look at these two diagrams. This one diagram 1 and this one here diagram 2, dear learners. When you look at the displacement, they are all moving in the same way. So we do say they are oscillating in phase. But could they be moving in the maybe for this one here, diagrammatically, this is how it should move, like particles oscillating in phase. They are all moving together. It will just act like one particle, but it's not really the case. Then we have what is called the phase and the phase difference. You need to understand these terminologies. So look at maybe again, allow I call this one diagram 1, this one diagram 2. When you look at PYZ and XYZ, both are XYZ, but we have particle P and Q. Particle P is moving from X to Y to Z and back, while Q is now moving in the opposite direction. So now, because the two are moving in opposite directions, then we say that the oscillations are 180 degrees out of phase because they are moving in opposite directions. So they are not in phase, but rather we term them to be out of wave or out of phase. And when you represent them here graphically, this is how you will find them aligning. This is how you will find them aligning. When one is moving from up, down, up, down, up, down, this one is moving completely out of phase in the opposite. This one is like that. You can see the movement. So that means they are out of phase completely by 180 degrees. Then look at these ones here. The waves are oscillating but are at 90 degrees, not 180, 90 degrees out of phase. To get the phase difference, if you have this one here, read the angle here and the angle here. When you subtract the value you get here from the value you get here, you should be getting what is called the phase difference. You should be getting what we call the phase difference. Now, learners, let's look at examples to seal our level of understanding. Waves on a spring are produced. I want a pen that can write better, maybe a green or a blue pen can even be better here. Waves on a spring are produced at the rate of 20 wavelengths every 5 seconds. Part 1, find the frequency of the wave. You know, for us to find the frequency, we need to understand the meaning of the term frequency. Frequency refers to the number of oscillations made in 1 second. Remember, I said the term, you can use the term oscillations, cycles, or waves, complete waves. So the number of oscillations made per second. Here you can see waves are produced at the rate of 20 wavelengths every 5 seconds. It means for 5 seconds, 20 oscillations are made. What about the number of oscillations made in 1 second? What about 1 second? I want to get the frequency. What about 1 second here? You cross multiply. So this will be 1 times 20 divided by 5. This is giving you 4. And because they want frequency, the SI unit for frequency, learners, is Hertz. 4 Hertz. That's why when you look at your answer, when you look at this one here, though they did not finish it well, but F is equal to 20 over 5, this should give you 4 Hertz when you simplify. Part B of the question. If the wavelength of the wave is 0.01 meters, find the speed. Remember we said speed which is given by V is equals to lambda F. Speed is given by lambda F. So they want the speed which is given by lambda. Lambda is the symbol for wavelength. Our wavelength here is 0.01. So this will be 0.01 times the frequency which we've obtained here is 4. When you multiply 0.01 times 4, you are going to get 0.04. And because it's velocity, it will now be meters per second. That's what you can see they found here as their answer, learners. Part C, periodic time, the period of the waves. Remember periodic time T, I say that T is equal to what? 1 over F. This will be 1 over our frequency which is 4. This will be 0.25 seconds. 0.25 seconds will be the periodic time. That's what you can see they gave here as their answer. So learners, that is how you are supposed to analyze those questions. Allow a look at the next example for better understanding once again. A water wave travels 14 meters in 4 seconds. If the frequency of the wave is 2 Hertz, number 1, determine the speed. Remember, for you to get speed, you need wavelength and frequency. So first of all, let's get what is called our water wave travels 12 meters in 4 seconds. We should be knowing, because we know that v is equal to lambda f. Part A, find the speed. Part B, the wavelength. When you look at speed, mathematically, learners, your teacher must have told you that speed can be given by taking the distance divided by time. So the distance, the water wave travels 12 meters, so the distance will be 12 meters divided by the time 4 seconds. So this is going to give you a speed of 3 meters per second, and that is the speed of the wave. That is simply how you get the speed of the wave. Part B, the wavelength. Now when you know that v is given by lambda f. Our speed is now 3, v is 3, is equal to lambda, which is the wavelength which we are looking for, times the frequency, which is 2. So this is going to be 3 will be equal to 2 lambda. To get lambda, you divide 3 by 2. So lambda will be given by 3 over 2. So this will be, my lambda is going to be 1.5, because it is wavelength, so it will be meter. 1.5 meter. 1.5 meter. That is how you respond to that. And when you look at it, you can see they also got it right here. Let's look at now this one here, a very interesting one. Please make sure you pay a lot of attention, because this one is quite involving, and I'm sure I'm going to simplify it so that you understand the concept. I'm here for you. If you find STEM Smart Academy supportive, please make sure you subscribe, like, and share. Tell your other friends also about our channel. The figure below shows a waveform in a string. The numbers in the diagram shows the scale in centimeters. The speed of the wave, we've been given the speed here as 10 meters per second. Look at your diagram. Part A, they are saying, with reference to this motion, determine the amplitude. A very smart learner has to know that this is a transverse wave. A transverse wave. Number 2, you have to identify what we normally call what? The mean position. This one here, this horizontal line, is what is called the mean position. I'm seeing there is wrong calibration. This value here should be 0, not 5. Part A, with reference to this notion, determine what is called the wavelength. When you are looking for the wavelength, learners, what are you considering when you are looking for the wavelength? Remember, learners, what did we say is the definition of the term wavelength? Can be the distance between two troughs or two crests. If I talk about a trough, maybe a crest, this is a crest and the value here is 20. Another crest comes here and the value is 40. So the distance here, this is 60. So 20 minus 6 to get 40. So meaning your wavelength is 40 meters. Because remember we said that wavelength is the distance between two successive crests or troughs. When I will refer maybe to troughs, here the reading here will be 0. The next trough is here whose reading is 40. So from 0 to 40 you get that is it. Part B, the amplitude. What did we say about amplitude? We said the maximum displacement of a wave from the mean position. This is the mean position. So this maximum displacement on either side, you can see the value 5 or negative 5. So the amplitude here is 5 centimeters. If the unit there was centimeters. I'm also saying this one here should be centimeters, 40 centimeters. Let's look at part C, frequency. For you to determine frequency, remember, there is something we had said. Let me look at this. We have already the speed here. We had said that V is equal to lambda f. What is our speed? Our speed is 10 meters. Should be equal to the wavelength of our wave. What is the wavelength? Our wavelength, just a moment. Our wavelength is 40 centimeters. When you convert it to meters, you divide by 100. So this will be now 0.4 times f. It will help me to get my frequency. This means my frequency will be given by 10 divided by 0.4. 10 divided by 0.4. When you take 10, you divide by 0.4, you are going to get 25. And that will be your frequency. So your frequency here is 25 Hz. Number next, you are told to get what? The period of the wave. Remember, t is given by what? 1 over f, which is 1 over 25. And when you take 1 divided by 25, you are getting 0.04. 0.04 seconds. So this one here will be 0.04 seconds. So that is what you can find these guys also gave. That is what they gave. So that with me, I've finished doing the topic, but I can leave for you an assignment. You can see those questions, you can copy and attempt your own. You can copy and attempt your own. Question 1, question 2, all these you can attempt. They are doable. They are doable, dear learners. You can see very good, nice questions. Where you don't understand, feel free to come and consult. All this is well catered in STEM Smart Academy. All this is well catered in STEM Smart Academy. Thank you for being part of us. Subscribe, like, and share. Tell your other friends about STEM Smart Academy. It has been my pleasure having you in this topic. We've come to its end. We've come to its end. Thank you. See you next time in our next session. Goodbye for now, dear learners.